Welcome to this third lecture in this NPTEL course on fluid mechanics for undergraduate students in chemical engineering. In the first two lectures, we introduced this course by telling you how chemical engineering is important, how fluid mechanics is important in chemical engineering, and chemical process industries, and why chemical engineers have to have a thorough understanding of fluid mechanics in order to design many chemical processes better. Okay. And we also told you the approaches that one normally takes in understanding fluid flows for chemical engineering applications. We said that there are macroscopic approaches wherein one writes integral balances of mass, momentum and energy, and then there are microscopic approaches where one derives differential equations that are valid at each and every point in the flow. And then when these two approaches are not workable in a very complicated industrial setting, there is also the need for experimentation, and there we said that dimensional analysis will play an important role in using in properly designing experiments and using those experimental results for scaling up of results from a lab scale to industrial scale. So, after introducing the course, we also gave a brief outline of what are all the topics that we are going to cover in this course, and after that we introduced the system of units that we are going to follow, SI units. That we are going to follow the SI units in this course, which is the conventionally accepted units everywhere in this scientific world. And we also told that if there are other systems of units that are being used in some contexts, then there are ways of converting from SI units to the other units if you need to convert them. Okay. Finally, in the last lecture, we started our discussion on the framework that we are going to use to analyze fluid flows in chemical process industries, and that framework is called the Continuum Approximation. It's called the Continuum Approximation. What this approximation says is that in a flow, for example, if you are interested in a flow in a very long pipe, which is schematically shown. So, there is flow. If you have flow in a very long pipe, okay, in principle the continuum approximation says that you can define velocity at each and every point in the flow. Okay. The continuum approximation says that you can define velocity, density, pressure or any fluid property, temperature, as a smooth and continuous functions of spatial coordinates we will see that in order to analyze any problem in fluid mechanics, you have to first set up a proper coordinate system. For example, here a simple rectangular coordinate system. Okay. So, here for example, if you have density, density is a smooth continuous function of x, y, z, the three spatial coordinates in the rectangular coordinate system, and time. Okay. So, the key thing is it is a smooth function, continuous function that is defined at each and every point. So, all these quantities, velocity is a vector, it has both magnitude and a direction. Velocity is also a function of all the three spatial coordinates, and t is time. Okay. So, what the continuum approximation says is that you can plot all these properties. If you take density as a function of x, it says that you can plot this as a function, as a smooth function. So, the question is, first of all, why is this approximation being made? We saw that a fully molecular approach that one can conceive, because we said that a fluid ultimately, be it a liquid or a gas, is ultimately comprised of molecules. So, one is tempted to first go for a fully molecular approach. So, even if you consider any reasonable macroscopic volumes that are encountered in any practical application, you will have the number of molecules to be a very large number. It is of the order of Avogadro numbers 10 to the 23 in a very reasonable volume, okay, in any practical application. So, this is a huge number. So, it is not possible to solve the motion of all these huge number of molecules to obtain, for example, quantities of practical interest to us, such as forces that are experienced by the walls of the pipe and so on. For example, if you want to pump a fluid in this pipe, okay, the reason why you need a pumping cost is because of the drag force exerted by the surrounding walls on the fluid flow. So, if you want to estimate or predict the pumping cost, you have to know, you have to have an idea of these forces. So, ultimately these forces are due to the molecular interactions that are there, but it is simply not possible to compute the forces exerted by each and every molecule on the surface of the wall, because simply because of the huge number that is present. Okay. Even if you have that information ready, even if you were to solve for all these forces, such an information is not really required, because all we require is the total force, and we are not overly concerned in engineering studies as to which molecule is exerting a force. All we are interested in design is the force that is being experienced by a solid surface, for example. So, a fully molecular approach, we said in the last lecture, is not feasible generally, and even if it were to be feasible, it is not necessary in most practical applications, in engineering applications. Okay. So, a fully molecular approach is not necessary or feasible. So, we rule that out. Then the only other option is this continuum approximation, where we completely ignore molecular details and treat the fluid as a continuous medium, wherein with respect to a coordinate system, at each and every point in space, various quantities such as density, pressure, velocity, temperature, concentration, all these are defined at each and every point, and therefore, you can, and these are assumed to be smooth and continuous functions of all these spatial coordinates and time, and this is the continuum approximation. Now, whenever we make an approximation or an hypothesis, it is first useful to see the domains of validity of the hypothesis. Okay. So, how do we go about doing that? Okay. Let us take again this case of a pipe flow. Okay. You have this pipe, which is very commonly encountered in chemical industry. Okay. And let us say that we are interested in the, suppose we are interested in defining the velocity density of the fluid at each and every point in the pipe. Okay. So, we first put a coordinate system. This is called a rectangular coordinate system. There are 3 mutually perpendicular axes. Okay. And so, you want to define in the continuum approximation, within the continuum approximation, quantities like density at each and every point in the pipe. What do we mean by density at each and every point in the pipe? Well, let us take a point. Okay. This point A is labeled by the coordinate x, y, z. For example, if you were to construct a position vector, okay, so it will have a label x, y, z. Okay. So, you want to tell, you want to see what do we mean by, we want to understand what do we mean by density at this point. So, how do we calculate density at a point? Well, a point really has no volume. So, we cannot density. Okay, first, before I say that, first, what is density? A fluid density, as we all know, is denoted by the Greek symbol rho, is mass per unit volume of the. So, you take a particular volume and measure the mass of the fluid present in the volume, divide the mass with the volume. So, this is the density, and in SI units it is kg per meter cube, that those are the units. Okay. So, here we are worried about density at a point has 0 volume. If there is 0 volume, then there is 0 mass. So, that does not make sense. So, what we mean by density at a point is that you take a point, let us say a point here, just for clarity, you take a point and construct a tiny volume around it. Okay. You construct a tiny volume. For simplicity, I am constructing a cubic volume. Okay. So, this cube has side delta L cube. So, that is the volume delta V. Okay. So, you take any point in the pipe. So, there is fluid flow in the pipe. You want to understand for simplicity, let us say density at a point. So, what is density at point A? So, let us call this A, okay, just because we have changed it. Okay. Let us call this point as A. Okay. So, density at point A, what is the density? Well, what you will do is you will count the number of molecules in that volume delta V. So, we will take the delta V, which is basically delta L whole cube in the denominator. You will count the number of molecules, let us call it as N, capital N, times the mass of each molecule. So, this is the total mass of, this is molecular mass, this is the total number of molecules in that volume. Okay. So, this will be the density at point A. Okay. So, but since we are saying the density associated with a point, we have to be careful in saying that this is in the limit as the volume delta V shrinks to a point, that is tends to 0. Okay. So, this is the way in which density is defined formally in a continuum approximation, that you take a point, construct a tiny volume, count the mass or count the number of molecules and find the mass divided by the volume. Now, clearly we cannot take, so firstly, in order for this to make sense, this delta V, the definition, in order for this definition to make sense, this density that we obtain, the numerical value should be independent of delta V. That is what we should expect, because if we find, if you calculate density at a point by considering one delta V, and if I calculate the density by considering a slightly different delta V, and if we come up with different answers, then density is not uniquely defined at that point. So, in order for the continuum approximation to make sense, the density, the numerical value of density that we obtain should be independent of delta V. Okay. Now, if that is the case, let us take the extreme cases. Okay. If that is the expectation that we have, then let us take delta V to be very, very small. Now, what do we mean by very, very small? Well, we know that a fluid is ultimately comprised of molecules. So, let us take, let A be the diameter of the molecules that comprises the fluid. So, first case, consider delta V to be very small. If A be the diameter of the molecules, then delta V will be roughly proportional to A cube. There will be some numerical prefactors, those are not of importance to us in our argument. Okay. So, if delta V is proportional to A cube, then you have a very tiny volume that is proportional to tiny volume that is comparable to molecular scales. Okay. So, if you consider such a tiny volume, okay, this is a tiny volume proportional to molecular volume, then at a molecular level the fluid molecules are not stationary or static, they are owing at any non-zero temperature, owing through thermal motion, they will be rapidly moving at very, very large velocities. So, the presence or absence of a molecule is a purely probabilistic event. Okay. So, if you consider a volume if you take a point and construct a volume about that point, and if that volume is comparable to molecular dimensions, then whether there are molecules or not itself is a probabilistic event. So, this is true even if the molecules, if the volume size is slightly larger, even if it is, let us say 5 times the molecular diameter, I mean just for the sake of argument. Okay. If delta V is proportional to 5 times A cube. Okay. Even so, then the number of molecules that are present. So, here there could be either one molecule or no molecule. Here there could be, let us say, few molecules, 3. if you are to consider the same volume element around that point at some other later time, this could have no molecules at all. So, the number of molecules in a very tiny volume, that is proportional to the molecular dimensions, is a highly fluctuating quantity. Therefore, the density that you will get, which is the number of molecules times the molecular mass divided by delta V in the limit as delta V goes to 0, okay, this will also be highly fluctuating if delta V is comparable to molecular dimensions. Okay. So, clearly there is a lower limit as to how small your delta V can be, because if your delta V is too small, density is not uniquely defined, because it will fluctuate very wildly. Okay. So, in the next slide, what I am going to do is to plot, if you were to do this as a thought experiment where you plot density, which is defined as limit delta V going to 0, okay, divided by delta V. Now, since I am going to discuss wide variations of delta V, it is useful to plot density as a function of a logarithm of delta V, okay, in the x axis, and I am plotting the density in the y axis. Now, what will I get? Now, when delta V is proportional to a cubed, very small, where a is the molecular diameter, okay, then density will be a wildly fluctuating quantity for the reasons I just mentioned. Now, as delta V increases in this axis, now that means that your volume about that point is increasing larger and larger. So, the density that is defined as number times molecular mass divided by delta V will slowly settle to a constant value, because if the volume becomes larger, the number of molecules that are present, which I am going to indicate now by several red dots, okay, even though it is still a fluctuating quantity, whether you add one more or one less should not largely affect the numerical value of density. Okay. So, even though n is still fluctuating, the fluctuations cannot play a big role in defining the numerical value of the density. Okay. So, as you increase delta V, you will find that the density will eventually settle to a constant value. Okay. Now, this is precisely because of the fact that fluctuations in n about the mean, about the average, they are proportional to 1 over root n. This is a fundamental result in statistics and statistical mechanics. This is goes by the name of central limit theorem. So, if the fluctuations in the number of molecules in a volume, if they decrease as the volume becomes larger and larger, and it decreases in the following way, it decreases as 1 over square root of n. So, if n is of the order of 10 to the 8, then the fluctuations will be of the order of 10 to the minus 4. So, it means that it is so small. Okay. This is the fluctuations in the average relative to the average. Okay. So, divided by the average itself. So, if n is 10 to the 8 and let us define the fluctuations with delta n, then delta n by n will be proportional to roughly 10 to the minus 4, or delta n itself will be of the order of 10 to the plus 4, because n is 10 to the 8 example. Okay. So, the fluctuations are small in when the size of the volume becomes larger and larger, but can we take the volume to be arbitrarily large? Okay. The answer is no, because eventually we remember the context was we took a pipe in the last slide, okay, and we took a small point, constructed a tiny volume, okay, about that point, and we are interested in obtaining a pointwise value for the density. Okay. Now, clearly and trivially speaking, if this is the diameter of the pipe, your delta V cannot be proportional to or comparable to d cube, because in which case then there is no point, you cannot speak sensibly of a point wise variation of density. So, clearly there are restrictions as to how large the volumes can be and how small the volumes can be. So, the continuum approximation works when we say, so let us say validity of continuum approximation. It works well when there is a, we say, separation of length scales. So, if you take a point and construct a cube of size delta L, okay, the volume is proportional to delta L cube, okay, then the continuum approximation wherein you can propose pointwise variations of you can define each physical properties at pointwise is valid when delta L, which is the side of this cube which makes the volume, is large compared to the molecular dimension. This is the molecular dimension, molecular diameter. This is the side of the cube which forms the volume. The test volume, and this should again be further, this delta L must be small compared to macroscopic lengths, for example, the pipe diameter in our illustration. Okay. So, this is when the continuum approximation is valid. Now, this is not true only for density, even if you were to consider, so we did this very briefly in the last lecture, let me remind you of that example. Even if you were to consider pressure, the pressure ultimately, if you consider a flat surface, pressure is the normal force exerted by the fluid, by a fluid on a surface per area of the surface divided by the area of the surface. So, if you consider pressure on a solid surface, this is a solid wall of area A, then why is there pressure? Suppose this solid wall is exposed to air, the pressure is there because of the collisions of molecules that are present in the air, in the gas with respect to the wall, and the collisions means that there is a rate of change of momentum. That rate, whenever there is a collision of a molecule with a solid surface, there is rate of change of momentum. That rate of change of momentum will manifest as a force on the surface, and that force divided by area A is the pressure. Okay. Now, again the continuum approximation means that, first of all, the continuum approximation works because even if you consider an area with which is made of a square with side 10 to the minus 6 meter, that is 1 micron, it is a very small, this is 1 micrometer. Okay. Even if you were to consider a tiny area, so suppose you were to use a pressure transducer or a pressure sensor, it will have a tiny area associated with it. Even if you were to consider a tiny area which you would think as so small that you can think of it as a point, within that area, from elementary kinetic theory you can that one learns in physical chemistry classes, one can show that the number of collisions, the average number of molecular collisions is proportional to, is of the order of, rather can be estimated to be about 10 to the 7 collisions per second. So, even in a given second there are so many large, there is such a large number of collisions that the surface of the sensor which is trying to measure the pressure will sense only an average of all these collisions, and it cannot resolve individual collisions. Okay. So, when you define pressure as force by this delta area in the limit as delta A goes to 0. So, let me erase here. Okay. What this means is that as you decrease delta A from this area to a smaller area, you will still find the value of the pressure to be uniquely defined. Okay. So, even if you change the probe dimension, okay, as long as you are not encroaching on the molecular scales, you will still find that the pressure is uniquely defined and it is independent of the test area. Okay. This is the same with density as well. In the previous example, we took different volumes and then we plotted. If you remember, what we plotted was that we took different test volumes and we tried to plot the density that one would compute in this test volume as a function of the size of the volume. Now, for molecular, when the volume is proportional to the molecular dimensions, then you found that in this regime the density is fluctuating, okay. But when the volumes are such that they are large compared to the molecular dimensions, but small compared to macroscopic dimensions, then you will find that the density is a unique value. That is, density is mass present in that tiny volume divided by the volume. So, it is defined as limit delta V goes to 0, delta V goes to 0, mass divided by volume. So, as you shrink the volume such that you still large compared to the molecular scales, the mass that is present in that volume will also decrease, but the ratio of these two will approach a unique value, that is the continuum density. Okay, this is the density as defined in the continuum approximation. Okay. And the same goes for the pressure, which we discussed in the next. So, the pressure will approach a unique value irrespective of the area, if the area is large compared to the molecular dimensions. Okay. So, this is the sum and substance of the continuum hypothesis or approximation. Now, once we define the continuum approximation, we can express density as a function of, as a smooth function of x, y, z and time. Okay. So, as an illustration, I am just showing that density can be plotted as a function of x with one spatial coordinate as a smooth function, and so is pressure as a function of, let us say, z, okay, and so on. Okay. So, this is how, once you define the continuum approximation, once we understand what we mean by values of density and pressure at each point, okay, we can sensibly define these quantities at each and every point in the fluid. Now, the discussion on the meaning of continuum hypothesis also tells us when continuum hypothesis can fail or continuum approximation can fail. Okay. Now, the molecular length scale in a liquid, the molecular length scale is simply the diameter of the molecules that are present in the liquid, because if you remember from your elementary physics or chemistry classes, a liquid is very, very dense. So, all the molecules are, so this is diameter A, are fairly close by with very little gap between them. Okay. Okay. So, the molecular length scale is the molecular length scale in a liquid is the diameter of the molecules. Okay. But if you consider a gas, the molecular length scale is not really the diameter of the molecule, because a gas, if you remember, is very dilute. So, the molecules are far well separated. Even though the diameter of the molecule is still A, the relevant length scale here in a gas is not the dimension of the molecule itself, but it is called the mean free path. So, let us denote it as Lm. So, this is the average distance between two molecules before they collide. Okay. Okay. This is called the mean free path. So, this is the average distance a molecule travels before it collides with some other molecule. So, this becomes this is denoted as Lm, this becomes the relevant molecular scale. Okay. Now, so this mean free path, okay, can become substantially large for what are called rarefied gases. Rarefied gases are gases with very low densities. Rho is very small. So, this can be achieved if you know what is the ideal gas law. For example, PV is nRT, where n is the number of moles. So, this is the mass divided by the molecular mass, okay, RT, and I bring the volume in the denominator. Mass by volume is the density. So, P is rho by m RT, where R is the gas constant and T is the temperature. So, when can you get low densities? When the pressures are low, okay, that means that density is low, because pressure is directly proportional to density in a gas. So, densities, these are not these are encountered in some applications when the pressure is so low, the density becomes very small, then the mean free path becomes large. If the mean free path becomes very large, by very large we mean that the mean free path, if mean free path becomes comparable to the macroscopic dimensions. For example, you have flow of a rarefied gas in a channel with diameter or length h, and let us say the mean free path is of the order of h, okay, then you will find that continuum approximation fails, or it becomes questionable because you can no longer define sensibly point-wise quantities in this case. Okay. So, so in rarefied gases one has to be careful. Okay. You should, I mean, this is a warning. So, beware of using the continuum approximation. Another context is in applications, there are in recent years there are what are called microfluidic devices, which are used in several biological and biotechnological applications. These are made of channels, okay, and whose the gap in which fluid is flowing is itself of the order of, let us say, 100 microns or 10 microns. Okay. If the fluid which is flowing is comprised of molecules which are not small, which are, if the fluid itself has large molecules like polymeric molecules, then the molecular dimension becomes comparable to the channel dimensions, channel width. So, again continuum approximation becomes questionable, the use of continuum approximation. So, there are cases where the length scales, the molecular length scales become comparable to the macroscopic scales, as in rarefied flows or microfluidic flows. In such cases, it is not obvious that whether one can successfully use continuum approximation, and there are always other more fundamental approaches where one takes a full molecular approach, full molecular detail, but those are obviously much more involved, and they are so they are specific to the kind of problems that one addresses. But in general, okay, continuum approximation can be safely used, okay, in many engineering applications and almost all engineering applications, conventional engineering applications, where there is the macroscopic scale is very large compared to the pipe diameter or the tank in which the fluid is stored, or if you have flow past a sphere, the diameter of the sphere over which the fluid is flowing. Okay. If those macroscopic dimensions are very large compared to molecular dimensions, okay, which is normally valid in engineering circumstances, then one can safely apply the continuum approximation. Okay. So, this completes my discussion of what the framework that we are going to use. So, once you use that framework, the continuum framework, we will define velocity as a function of all the 3 coordinates in the fluid in the coordinate system, and time, pressure as a function of all the 3 coordinates and time, and density as a function of smooth functions of all the 3 coordinates and time. These are called fields, continuum fields. Okay. So, these go by the name of fields. So, and we assume that they all can be differentiated easily, they are differentiable, smooth and continuous. Okay, now that we have understood the limitations and validity of continuum approximation, it is the right time to define what a fluid is. Okay. So, in order to understand what a fluid is, it is useful to contrast the mechanical behavior of a fluid with that of a solid. So, let us begin with so that we can compare and contrast the two behavior, how fluid responds under applied forces and how a solid responds under applied forces. Okay. So, let me say fluid versus solid. Okay. So, let us first consider the case of a solid which is elastic in nature, for example, a piece of rubber that one uses to erase. So, example is eraser. Okay. So, imagine, let us take a block of solid. So, this is a block of solid, this is a piece of rubber that we are going to use in our thought experiment. Okay. So, this dimension, let us say W, is very large compared to this dimension which is H. W is very large, it is about let us say 20 or 50 times H. So, we need not worry about variations in the third direction. So, let us just consider the solid to be in the plane. Okay. So, let us just consider the piece of solid like here, and of course, I am putting a coordinate system as usual. In order to analyze any problem, we have to first set up a coordinate system. Okay. So, this means the z is the coordinate that is coming out of the board. So, variations in z coordinate are not important. Okay. So, we are considering a solid, therefore, and we are taking a cross section at any plane that is perpendicular to the z direction. So, it will be in the xy plane. Okay. Now, imagine that this piece of rubber is placed between two plates. Okay. The top plate, this is the bottom plate. Okay. And let us say the bottom plate is stationary, this is a solid, and the top plate you are applying an external force. Okay. And this force is being applied in the x direction. Okay. This is the x coordinate. Okay. The force is being applied in the x direction. Now, in mechanics, in both fluid and solid mechanics, if you have a surface, remember I am just drawing here the cross section at any plane that is perpendicular to z. Okay. This force is actually applied on a surface, okay, on the top surface of this piece of solid. Okay. And if the area of the top surface is A, then this Fx by A is called the stress. Okay. Now, one normally distinguishes between two types of stresses. This is called the shear or tangential stress, because this is tangential to the surface on which the force is acting. So, if you have a surface, this is the surface. Okay. This surface has a unit normal, let us say j is the normal in the, so if you have a coordinate system I, j and k, or the 3 unit normals in the x, y and z directions. So, the unit normal of this surface is j. Okay. Now, but the direction of the force is parallel to the surface and not in the direction of the normal, it is perpendicular to the normal, it is parallel to the surface. Okay. So, these are called shear stresses. So, we are applying a shear stress, a force that is applied parallel to the surface per unit area. Now, if this is in contrast to, suppose if I have a surface again in whose unit normal is in the j direction, and if I apply a force like here, this is a compressive force, this is called a normal stress because the force is applied along the normal. So, here it is applied in the direction opposite to the normal. So, whether your the magnitude of the direction of the force can be either in the plus j or minus j direction, that is immaterial, but essentially it is a force in the direction of the normal. So, it is a normal stress, whereas the tangential, if the force is applied tangentially, it is called the shear stress. So, this is the experiment we are doing. We are taking a piece of rubber and then we are placing it between two plates. The bottom plate is stationary, top plate you are applying a tangential force, and the tangential force per unit area is the stress. Now, if you were to do this experiment, what is going to happen? Okay, that is the thing, that is a question we are going to ask. So, you have these two plates, okay, and you have a material, the thickness of this material is h, and as you know, this is the xy plane, we are not worrying about the variation in the z direction. Okay. So, you have, let us say, before applying stress, any stress, so the solid material is in the stress free state. Okay. What we do is that we take this piece of material which is not being acted upon by any stress, okay, it is in a stress free state. So, let us apply, let us mark various points with a colored dye or whatever. Okay. Let us imagine that we can mark points on a cross section of the solid with some colored material, okay, and imagine what will happen to this, the same system when you now start applying stress. Okay. So, okay. So, this is the location of the points in the undeformed state or the stress free state, okay, undeformed location of points. Now, you are going to apply a stress in this direction. Now, there is no stress that is being acted in the bottom direction, bottom plate, sorry, and some stress is being applied in the x direction in the top plate f x. So, what will happen to these points? Okay. In a solid responds to applied forces by undergoing some deformation. So, all these points will move by deformation, we mean that these points will start moving from their undeformed locations. Okay. So, the green points refer to deformed location. We say that the solid responds to applied stresses by undergoing deformation. By deformation, we mean that various points that were there in the solid before the application of stresses will start moving to some other new point, will move to some other new point, but they will stop moving because after you start applying stress, once the solid starts deforming, internal stresses develop in the solid which will resist further deformation. Okay. A solid will not deform continuously, the points will deform to some extent and then stop, and this is a very quick process in a solid. So, it deforms and then it stops deforming, and the deformed location of points is given by the green points. Okay. Now, so let me do this in a more quantitative way. So, you have the undeformed thing and the deformed thing. Okay. So, this angle, okay, since there is no force in the bottom plate, okay, no force. So, this point will remain here itself, whereas this point would have moved because you are applying a force here, a tangential force here. Now, this deformation can be characterized by an angle delta alpha, because if you apply a very small force, okay, then that means that the amount of deflection of this blue line of this, let's draw it with a green line, okay, the amount of deflection that you will experience is very small. So, this delta alpha is a measure of what is called the strain in the solid, because a solid undergoes some deformation upon in response to the applied stress, but it does not continue to deform, it merely stops deforming because of the internal stresses. So, in a solid, if you do experiments, suppose you were to do an experiment, let us say you apply Fx1, the force Fx1, and you divide by the area over which the force is applied, and then you will find that if you were to do these experiments, okay, so let's write this in the left side, in the right side. So, suppose you have to apply a force Fx1 and you are applying it over an area, and if you measure the deflection delta alpha, okay, if you apply a value of Fx1, let us say you find a deflection of delta alpha 1 and Fx2, and you will find some other deflection delta alpha 2, and if you were to plot all this, you will find that Fx by A is proportional to delta alpha. You will get a straight line, okay. When there is no force, there is no delta alpha, so it starts at 0, okay, and it is a linear, it is a straight line, it is directly proportional. So, you will find for elastic solids, if you were to do these experiments for purely elastic solids, this Fx by A is called the stress, and stress is denoted by the Greek letter sigma, okay, and you will have x being the direction of the force, which is one subscript, and y is the direction of the normal over which the force is acting. Okay. Remember that we are having this surface whose unit normal is in the j direction and the force is acting in the I direction, which is x. Okay. That is why there are two indices, one is the direction of the force. So, this is called a shear stress. Okay. This is a shear stress because the force is acting tangentially to the surface, it is not acting in the normal direction of the surface. So, this is a shear stress, force per unit area. You will find that this is proportional to, okay, since I am using alpha, so I do not want to use, so let me use, this is a proportionality sign, it is proportional to delta alpha. Okay. So, this is what one will find, okay, if we are to do this experiment for a solid. The stress is directly proportional to strain in a solid. Okay. So, for an elastic solid, stress is proportional to strain. Okay. So, let us draw this picture again. So, you have these two plates and you have a piece of solid, a rubber, let us say, and then you found that before deformation things were in the red line, after deformation things were in the green line, and this angle is delta alpha. Okay. Now, this distance is h, let this displacement be delta L. Okay. So, this is the force Fx that is acting on a surface whose unit normal is in the y direction. Okay. Now, from geometry, tan delta alpha is delta L by h, but when delta alpha is very, very small, for small forces you will expect that the deflection delta alpha and the displacement delta L is small, is very small, then tan delta alpha is roughly equal to delta alpha. Remember that tan delta alpha is sin delta alpha by cos delta alpha, and as delta alpha becomes small or tends to 0, cos delta alpha tends to 1 and sin delta alpha is proportional to delta alpha, it goes as delta alpha. Okay. So, therefore, tan delta alpha will go as delta alpha. So, this equation means that delta alpha is approximately delta L by H. Okay. So, sigma xy is proportional to delta L by H. This is called the strain, and the constant of proportionality is called the modulus of elasticity. This is for an elastic solid. This is an equivalent of Hooke's law of elasticity. It's essentially some statement of Hooke's law of elasticity. For elastic solids, the stress is directly proportional to strain, and the strain is measured by this deflection delta alpha, and the constant of proportionality is called the elastic modulus or modulus of elasticity. The stress has units of pascals because it is force per unit area. This is dimensionless, this is unitless or dimensionless because this is a ratio of two lengths. This has no units, it is a pure number. So, G will have units of pascals. Okay. Now, this is what a solid is. A solid responds by undergoing some deformation or strain upon application of some shear stress, and the stress is directly proportional to the strain in the solid. In the next lecture, what we will do is we will contrast the mechanical behavior of fluid upon application of external stresses and see how it is different from a solid. So, we will see you soon in the next lecture.